Okay, we're going to move on and talk about chapter 5, which is going to be, we're going to start out with a very short section on using exponents, and then we'll move on to graphing and evaluating polynomial functions. So let's just start out with a quick review of evaluating exponential expressions. And all I have here for this is simply a slide that shows some examples of different exponent rules. These are all things you should have done before, so it should just be some review. Let's go through one by one here. The first rule says that if I have the same base and different exponents and the two numbers are multiplied together, I can add the exponents. So for instance, if I have 3 cubed times 3 to the negative 1, I can write that as 3 squared, which is 9. It's a lot easier than taking 3 cubed, finding out what that is, 27, and taking 3 to the negative 1, figuring out what that is, and then realizing it's 9. The second one, so I have something with an exponent, and that whole thing is raised to another exponent. I can just multiply those numbers together. So if I have 3 squared, all raised to the third power, I can look at that as 3 to the sixth power, which is again much easier than squaring and then cubing. If I have two numbers multiplied together and the two of them together are multiplied, raised to the m power, some number power, then I can look at it as the first number to that power times the second number to that power. So for instance, if I have 2 times 3, which we know is 6, raised to the second power, that's the same as taking 2 to the second power and multiplying it by 3 to the second power. So 4 times 9, which is 36. Okay, so this is a situation when we can distribute the square, but that's because this is multiplication. It doesn't work for addition. We've talked about that. Okay, the next one is if I have some number to a negative power, that's the same. I can rewrite that as 1 over a to that power. So 3 to the negative 2 is really the same as 1 over 3 to the 2, which is 1/9. Anything to the 0th power is 1. If I have something to the m power divided by that same base to the n, I can just subtract the numbers. So 5 to the 4th divided by 5 squared is 4 minus 2, which is 2. So 5 to the 4th divided by 5 to the 2nd is 5 to the 2nd, which is 25. And then finally, if I have a fraction all raised to the same power, I can raise the numerator to that power and the denominator to that power. So 2/3 squared is 2 squared over 3 squared, which is 4/9. Okay, that's really all we need to say about properties of exponents. We'll do some practice on those. Okay, let's look at polynomial functions. So what is a polynomial? A polynomial is any function of this form. Now, this is going to be a little bit esoteric perhaps. A number times x to a power plus a number times x to another power plus a number times x to another power and so on all the way down to what the first power and no powers. As long as this first number isn't 0. If this first number isn't 0, then this doesn't really make any sense. Okay, so this is kind of an unimportant term. Okay. Let's look at this. Here's a polynomial. 3 is a number times x to a positive whole number power. That's the only requirement here. This must be a positive whole number, an integer, or a natural number rather, plus a half, 0.5, which is a number, times x to a positive integer, a natural number, minus 4. That's a polynomial. Okay, here's another polynomial. A number times x to a positive whole number power, minus a number, which is 1, times x to the first power, which is a positive whole number. Okay, here's another one. A number times x to the 6th minus a number times x to the 4th, minus 9. Okay, so you've seen these before. These are called polynomial functions. Here are some examples of not polynomials. 1 over x. We can't have a polynomial when x is in the denominator of a fraction. X can be in the numerator, but not the denominator. Not a polynomial. This part's fine right here, but not this part, not the square root part. That's not all right. Again, positive whole number power, that's good here, but this is not a positive whole number. 7/2 is not a whole number. Okay? So there's some examples of non-polynomials. Okay, how do we name them? So we name polynomials by their degree. The degree is the highest power of x. Okay, so here we go. What I have here is if the function is f of x equals some number, just a plain old number, okay? Well, the power of x is actually 0. There is no power of x, okay? So for instance, a good example of that would be something like f of x equals 2. All right, that's still a polynomial. It's kind of a trivial polynomial, but it's a polynomial. We call this type of function a constant function, and the shape is a line. The next one, you've seen these before. f of x equals a number times x plus or minus another number. This is what we're used to seeing, a linear function, and the shape is again also a line. So both of these have lines. The only difference here is this is a horizontal line, this is a non-horizontal line. You can hear Billy in the background, I know. She's saying hello to you guys. Okay, the next one is what we've been dealing with quite a bit, and that's a quadratic. I have an x squared as the highest power, then I have an x, so you don't have to have the x there. There's no rule that says that this number doesn't have to be 0, okay, or this number, but we know the highest power is x squared. So if the highest power is x squared, we call it a quadratic, and the shape is called a parabola. We've done that. So again, here's an example. That's a quadratic. Okay, now we get into power 3. When the 3 is the highest power of x, when we write it out this way, okay, we call that function a cubic, and we also call the shape a cubic. Okay, so after we get past the quadratics, all the names are the same as the shapes. Okay, if the highest power is 4, we call this a quartic, and again, we call the shape a quartic. You don't hear people use that word very often for the shape, but the people do use it. So if the highest power you see when I write up my polynomial this way is x to the 4th power, it's called a quartic. The next one up is a quintic. Okay, so degree 5 is a quintic. And again, all we have to have is something times x to the 5th power. We might have these other terms. We might not. They may or may not be there. Okay, it's okay as long as the highest power is x to the 5th. We call that a quintic, and again, the description would be of the graph would be quintic as well. And after that, we just start to calling them degree 6, degree 7, degree 8. There may be other terms that we use, that people use for the higher order terms, but for the most part, those are just the only ones we use. Okay, 1 through 5 is the only ones that actually have names. All right. So general shapes of polynomials. Here's the basic rule. A polynomial of degree n can turn around one less than the degree times. So let's take a look. If we look at degree 0, it never turns. As a matter of fact, it doesn't even go in any direction. It just goes flat. So it's not even making sense to turn around. So we don't really talk about that. Degree 1. Degree 1, 1 minus 1 is 0. So this can turn 0 times, which means that if it's going up, it's always going to go up. Never turns. Degree 2, well, 2 minus 1 is 1. So this can turn around once. It can start by going down and turn one time and go back up. Degree 3 can turn around at most twice. Okay, that means we can start by going up in this case. We can turn once, go down, and once and go back up again. Degree 4 can turn around 3 times, down, up, down, up. Okay, so 3 different ways it goes. Down, up, that's 4 times, but it turns 3 times. And degree 5, down, up, down, up, down. That's where the 5 comes from, but it turns 4 times. It turns once, twice, 3 times, 4 times. Okay? So that's how you get the basic shape of a polynomial. You'll notice a few things. The odd number powers, okay, 3, 1, 5, because they turn around an even number of times, okay, if they start by going in one direction, going up, they always end going up as well. So if they start by going down, they will always end by going down too. The even ones, if they start by going up, by coming from a positive direction, they'll end up by going back to that positive direction. And conversely, if they started by going down, if they started by going up rather, they would end by going in the same direction. Okay, so in some sense, the odd functions do this. Okay, they go kind of up and down, whereas the even functions go both up or both down. And that's just a quick introduction to the shapes of what polynomials look like. Okay, the last topic here. Oh, where's the page? The last topic here is evaluating polynomial functions. We're going to do this 2 ways. The first way you've probably done before, and the second way you probably have not done before. Here's the first method. The first method is plug in. If I give you a polynomial, here it is, and I ask, evaluate this when x is 3. That is to say, if I put a 3 in there, what happens? Well, here's the first way to do it. If I let x be equal to 3, I can put a 3 in there and I get 2 times 3 to the 4th minus 5 times 3 cubed minus 4 times 3 plus 8. What do I get? 3 to the 4th times 2 is 162. 3 cubed times 5 is 135. 3 times 4 is 12 plus 8. Simplify that and I get 23. Okay? It's a little messy. It's actually quite a bit of work, really, when you think about it. Okay? That's method number 1. Method number 2 is actually a little bit, it's sneaky, but it's pretty cool. And we call this synthetic substitution. Okay, so I start with this, and this is what I do. This is a little tricky, so watch carefully. The first thing I do is I'm plugging in the number 3. So I set up this new kind of chart like this. Okay, I put 3 up here in a little box. That's the number I'm putting in. I put 2 from there. I put a negative 5 from there. Notice there's no x squared. So since there's no x squared, I put 0. I have to put in a 0 there if I'm missing a term. It goes 4, 3, 0. Right? Then 1. So the 4 goes there, part of the negative 4, and then 8. Those are where those numbers come from. Okay? So once I get that set up, it's actually pretty easy. I put a little horizontal line down at the bottom, and now we go to. I'm going to try to use my slate here in order to do this, but it may not work, so I may have to do this longhand. Okay, yeah, you have to do it longhand. This might be a little more work than I initially anticipated. The first thing we do, step number 1, is to bring down the 2. Okay, so all this is as simple as copy the 2 down. Okay. The next step is to take 3 times 2, and we get 6. And that goes there. So 3 times 2 is 6. 3 times 2 is 6. Okay? Now, it's easy as now as adding. So we go negative 5 plus 6 is 1. Good. Now I take 3 times 2 is 1, so now I'm gonna do this here. Okay. Now I do the same exact thing. I go 3 times 1 is 3. Good. You with me? And I do 0 plus 3 is 3. Good. Now I'm going to do the exact same thing. I'm going to do 3, this 3 here, times 3 is 9, and that's going to go here. Uh-oh. Billy's getting a little upset. To finish this up soon. Okay. Now negative 4 plus 9 is 5. That goes here. And now I go 3 times 5 is 15. So what's 15 plus 8? 15 plus 8 is 23. Hey, and that's the same answer as I got doing it the other way. Right? So my answer is the number down here, and I'll highlight my answer in, pink, how's that? Oh, that's not a highlight. Yeah, it is. Boom. There it is. And that's my result. So it works this way. We have to line up our numbers correctly up here. Then we drop the first number down. And from there, it's very mechanical. We take 3 times 2 is 6. That goes here. Then we add. Negative 5 times 6 is 1. Sorry, negative 5 plus 6 is 1. Then we go 3 times 1 is 3. Then we add. Multiply. 3 times 3 is 9. Add. 5. 3 times 5 is 15. Add. And once you get to the very end, that's your solution. So f of 3 is 23. Same exact thing as before. Okay? This is going to take some practice. We'll do a bunch in class. But this is a pretty cool way to be able to substitute. It does not require you to take 3 to the 4th power, which is awesome. Okay? It all requires a simple addition and multiplication in order to get the exact same result. All right, everybody. Good work. Thanks. I'll see you in class.